For most of Earth's history, life has unfolded quietly. Oceans filling with simple organisms, forests spreading slowly across land, creatures appearing, changing, and disappearing so gradually that no single moment feels decisive. From a distance, it can seem like a steady process of growth, variety, and persistence. And yet, hidden within the rocks beneath our feet, there are interruptions. Rock layers where once common fossils suddenly stop appearing, ecosystems that had remained stable for millions of years thinning, then breaking down. Long stretches of time where the familiar rhythm of life is disrupted, replaced by conditions that are harsher, simpler, and far more uncertain. These moments are not defined by single days or dramatic instants, but by slow changes that ripple across the planet over immense spans of time. Scientists refer to these intervals as mass extinctions, not because all life disappears, but because the balance that normally holds ecosystems together begins to fail. Species that once seemed secure fade away. Entire branches of the living world quietly come to an end. What remains is not emptiness, but a reduced and reshaped version of life, adjusting to unfamiliar conditions. If you enjoy these quiet journeys through deep time and big questions, you are very welcome to subscribe and join the Sleepy Scientist. And if you feel like it, sharing where in the world you're listening from tonight can be a gentle reminder of how far these thoughts travel. The fossil record shows that this kind of disruption has happened not once, but 5 times. 5 long periods when Earth's environment shifted so deeply that life was pushed close to its limits. Oceans lost oxygen. Climates drifted toward extremes. Volcanic activity altered the atmosphere. Continents moved, currents changed, and the conditions life depended on slowly unraveled. What emerges instead is a picture of change unfolding over immense spans of time. Living systems can be fragile under pressure, yet remarkably persistent. The planet does not reset or begin again. It shifts gradually, carrying remnants of earlier worlds forward into the present. What makes these events especially striking is not only how much was lost, but how much endured. Small, unassuming organisms often survived while larger, more dominant forms disappeared. Life did not recover quickly or dramatically. It waited. It adapted slowly. Over vast stretches of time, it filled empty spaces in unexpected ways, reshaping ecosystems that could never have been predicted from what came before. Understanding mass extinctions means stepping away from human timescales. These changes unfolded so slowly that no single generation would have recognized them as extraordinary. Each moment would have felt subtle, slightly fewer familiar forms, slightly altered conditions, a gradual sense that the world was no longer quite the same. By studying rocks, fossils, and chemical traces preserved in ancient layers, scientists have pieced together these deep time patterns, not perfectly and never completely, but with enough clarity to see how stress builds, systems weaken, loss accelerates, and then, long after, life reshapes itself once more. Tonight's journey moves through those 5 great disruptions, not to dwell on destruction, but to understand resilience, to explore how life continued when conditions narrowed, and how the living world repeatedly found ways forward without urgency, intention, or awareness of what was unfolding. Settle in, let time stretch, and allow Earth's long, patient history to unfold slowly. A mass extinction is not identified by a single dramatic layer of bones, or by one unmistakable moment where life simply stops. Instead, it reveals itself slowly, through patterns that only become visible when Earth's history is viewed from far enough away. To understand how scientists recognize a mass extinction, it helps to imagine the planet's surface as a vast archive. Over immense spans of time, sediments settle at the bottoms of oceans, lakes, and shallow seas. Dust drifts down, tiny shells accumulate, mud hardens into rock. Each layer forms quietly, recording what was living at the time it was laid down. Together these layers stack into a vertical timeline, with the oldest pages at the bottom and the most recent ones near the top. Within those layers, fossils appear. Sometimes they are large and easy to recognize. Often they are microscopic. Sometimes they are abundant, filling entire slabs of rock. At other times, they are rare, scattered, and subtle. What matters most is not any single fossil, but how groups of fossils change as the layers progress. In most parts of Earth's history, species come and go at a relatively steady pace. A few disappear, new ones emerge, others shift slightly in form over long periods. This slow, ongoing turnover is known as background extinction. It is the normal rhythm of life, driven by competition, environmental change, and the simple fact that no species lasts forever. Against this steady background, mass extinctions stand out because the pace changes dramatically. Instead of a few species fading away here and there, many disappear within a comparatively short slice of geological time. Groups that were once widespread and successful abruptly become rare or vanish entirely from the record. The usual balance between loss and replacement breaks down. When this pattern appears across many different environments and many different kinds of organisms at once, scientists begin to take notice. Importantly, these events are not identified by guessing or assumption. They are detected by careful counting and comparison. Paleontologists track how many species are present in one layer, then how many persist into the next. They look for sharp declines that cannot be explained by gaps in sampling or local conditions. When the same pattern appears across different continents, ocean basins and fossil groups, the signal grows stronger. Rock layers themselves offer additional clues. A sudden change in sediment type might suggest a shift in sea level. Dark, organic, rich layers can hint at low oxygen conditions in ancient oceans. Layers rich in volcanic material may point to prolonged eruptions that altered climate and chemistry. None of these features alone prove a mass extinction, but together they help build a coherent picture. Chemical signatures preserved in rock add another layer of evidence. Certain elements and isotopes behave differently depending on temperature, oxygen levels, and biological activity. When these chemical markers shift rapidly across a narrow span of layers, they suggest that Earth's systems were under unusual stress. Oceans may have warmed or cooled significantly. Atmospheric composition may have changed. Nutrient cycles may have been disrupted. These chemical changes are especially valuable because they record processes that fossils alone cannot show. Not all life leaves behind hard parts. Entire ecosystems can be altered without producing dramatic skeletons to mark the change. Chemistry helps fill in those quieter stories. Even with all this evidence, identifying a mass extinction is rarely straightforward. Rock layers can be incomplete. Erosion can remove pages from the archive. Some environments preserve fossils better than others. Scientists must constantly ask whether an apparent disappearance reflects a real biological loss or simply a gap in preservation. This uncertainty is not a weakness of the science. It is a reminder of how careful interpretation needs to be. Because of this, mass extinctions are defined not by exact numbers carved into stone, but by converging lines of evidence. A steep rise in extinction rates compared to the usual background pace, a broad impact across different environments, independent signals from fossils, sediments, and chemistry pointing in the same direction. Only when these pieces align does the picture become convincing. Another important detail is that mass extinctions are not moments. They are intervals. Even the most abrupt of them unfolds over thousands to hundreds of thousands of years. From a human perspective, that is unimaginably long. From a geological perspective, it is brief enough to appear as a sharp boundary in rock. This difference in scale is part of what makes mass extinctions difficult to intuit. They are slow enough that no single generation experiences them as a singular disaster, yet fast enough to permanently reshape the course of life. Framing extinction as a pattern rather than a moment helps avoid misleading images of sudden annihilation. There is rarely a clean line where everything on one side lives and everything on the other side dies. Instead, populations decline unevenly. Some regions are hit harder than others, some groups vanish early, others linger, only to disappear later as conditions continue to change. Survival, too, follows no simple rule. It is not always the strongest or the most complex organisms that endure. Often, it is those with flexible diets, broad tolerances, or modest needs. Sometimes survival seems almost accidental, shaped by geography or timing rather than any obvious advantage. From the fossil record alone, it can be difficult to say why one lineage persisted while another did not. This uncertainty is an essential part of how scientists approach mass extinctions. Rather than offering tidy explanations, research often narrows down possibilities. Evidence may suggest that climate change played a role, but not explain exactly how it affected every ecosystem. Volcanism may be implicated, without revealing all the pathways through which it caused stress. Asteroid impacts may leave unmistakable traces, yet still raise questions about why some groups survived the aftermath. Scientific humility emerges naturally from this complexity. Each discovery answers some questions while opening others. New fossils can refine timelines. Improved dating techniques can sharpen boundaries. Advances in chemistry can reveal previously invisible shifts. But the full story is never complete. Earth's past remains partially hidden, not because it is unknowable, but because time erases details as it preserves others. Seen this way, mass extinctions are not anomalies interrupting an otherwise stable history. They are part of the planet's long pattern of change. Life responds to shifting conditions, sometimes gradually, sometimes under intense pressure. Most of the time, those responses stay within familiar limits. Occasionally, they do not. When extinction rates spike far beyond the background rhythm, when ecosystems lose their usual structure, and when environmental signals align across the globe, scientists recognize that something unusual has occurred. Not a single event frozen in time, but a period when Earth's systems moved out of balance together. Understanding what a mass extinction really is begins with letting go of the idea of sudden endings. What appears instead is a slower, more complex process, one that unfolds across layers of rock, across chemical traces, and across the quiet absences where familiar forms no longer appear. It is in those patterns, rather than in any single dramatic moment, that the true shape of mass extinction becomes clear. Long before forests shaded the land or animals left footprints in mud, life was already busy shaping the planet beneath the surface of the sea. For hundreds of millions of years, the oceans were the only stage where complex life played out its quiet experiments. No wings, no voices, no eyes lifted toward the sky. Just water, light filtering down from above, and a living world arranged in layers. The earliest complex ecosystems were built almost entirely in the oceans. Shallow continental seas spread across much of the planet, warmed by sunlight and rich in dissolved minerals. Along their floors, communities formed that would feel unfamiliar today, yet followed patterns that still echo through modern ecosystems. Soft-bodied organisms drifted or anchored themselves to the seabed. Some filtered tiny particles from the water, others grazed slowly across microbial mats. Shells began to appear, offering protection and structure, and with them came new relationships between predators and prey. Nothing moved quickly. Energy flowed gently through these systems, recycled again and again by organisms that rarely strayed far from where they began life. Balance emerged not through strength or speed, but through repetition. Species occupied narrow roles, finely tuned to stable conditions. Temperature changed slowly. Ocean chemistry shifted gradually. Sea levels rose and fell over long spans of time. Within those boundaries, life diversified, filling available spaces with quiet efficiency. Coral-like organisms built reefs that sheltered countless smaller creatures. Trilobites crawled across the seafloor, their segmented bodies suited to both protection and movement. Brachiopods anchored themselves in place, opening and closing shells to feed. Crinoids lifted feathery arms into gentle currents, collecting food that drifted past. Above them, early fish-like creatures moved through the water, still experimenting with the idea of a backbone. None of these organisms knew they were part of something fragile. From within the system, everything likely felt stable. Generation after generation followed familiar patterns. Reproduction, feeding, growth, and death unfolded in predictable ways. The ocean seemed vast, forgiving, and endlessly accommodating. Yet that sense of stability rested on a delicate foundation. Early marine ecosystems depended heavily on precise conditions. Oxygen levels needed to remain within a narrow range. Temperatures could not swing too far or too quickly. Nutrients had to circulate without becoming either scarce or overwhelming. Because life was largely confined to the oceans, disruptions to water chemistry or circulation could ripple widely and efficiently. Unlike later ecosystems that spread across land, sea, and air, these early communities were concentrated. A change in sea level could erase shallow habitats across entire continents. A shifting climate could alter currents that connected distant regions. When stress appeared, there were fewer places to escape. Even so, life proved remarkably capable of building order from simplicity. Food webs formed that linked tiny plankton to larger grazers and predators. Waste products from one organism became nutrients for another. Microbes played a silent but essential role, recycling material and regulating chemical balance long before anyone could have guessed their importance. There was no single dominant species. Diversity expressed itself through form and function rather than size or intelligence. Many organisms looked strange by modern standards, shaped by evolutionary paths that would later end entirely. Others would leave descendants that persist in altered forms today. Importantly, all of this unfolded long before animals ventured onto land. The continents were largely barren, shaped by wind and water but untouched by roots or burrows. Without plants to stabilize soils, sediments washed easily into the sea. Rivers carried nutrients that fed marine life, but also made ecosystems sensitive to changes far upstream. From a distance, this world appears peaceful. No roaring predators, no sudden collapses, just slow movement and quiet interaction. But peace does not mean invulnerability. The same conditions that allowed early ecosystems to flourish also made them susceptible to disruption. Because many organisms relied on similar resources and lived within similar environments, stress rarely affected just one group. When oxygen levels dropped, entire communities struggled. When temperature shifted, species adapted slowly, if at all. There was little redundancy built into these systems, and little room for rapid adjustment. This fragility is not a flaw. It is a natural feature of early complexity. When life is still exploring possibilities, it often settles into patterns that work well under stable conditions, even if those patterns leave little margin for change. Geological evidence suggests that for long stretches, the oceans maintained a workable balance. Sea levels rose and fell without catastrophe. Climate cycles came and went gradually. Life adapted at a pace that kept ecosystems intact. The fossil record from these times shows continuity more than disruption, with familiar forms appearing layer after layer. But beneath that continuity, pressures slowly accumulated. The planet itself was changing. Continental plates shifted positions. Volcanic activity altered atmospheric composition. The distribution of sunlight across the globe evolved as land masses moved. None of these changes were sudden in human terms, but over millions of years their combined effects became significant. As continents clustered closer to the poles, ice began to form more readily. As ocean circulation patterns adjusted, oxygen distribution changed. As weathering rates altered, the flow of nutrients into the seas shifted. Each change alone might have been manageable. Together they began to test the limits of early ecosystems. Life responded, as it always does, through gradual adjustment. Some species became more common, others declined. New forms appeared at the margins, yet the overall structure of marine communities remained recognizable, giving the impression of resilience. From the perspective of the organisms living at the time, nothing dramatic announced what was coming. No warning signs, no sudden boundaries, just a world that very slowly became less forgiving. This is an important point when thinking about mass extinctions. The conditions that precede them often look much like ordinary life. Ecosystems function, diversity persists, balance holds, right up until it does not. The difference between stability and collapse can be subtle, emerging only when viewed across immense spans of time. Before the first great loss, life had already achieved complexity, cooperation, and efficiency. It had built systems that worked, sustained by narrow environmental tolerances and long-term stability. Those systems were not weak, but they were specialized, and specialization, while powerful, can reduce flexibility when conditions shift. In this ancient ocean world, life thrived quietly, unaware that it was approaching one of its earliest tests. The stage was set not by sudden violence, but by slow planetary change. What followed would not erase life from the seas, but it would challenge the assumption that stability could last indefinitely. For now, though, the water remained full. Reefs grew. Shelled creatures filtered the currents. Food webs held together through countless generations. The oceans carried life forward, balanced delicately between endurance and vulnerability, waiting for the planet to make its next move. The first mass extinction did not arrive with fire from the sky or sudden violence. It came quietly, carried in changes so gradual that life continued its daily routines while the world slowly shifted beneath it. During the late Ordovician period, Earth was a warm planet. Shallow seas spread across much of the continents, creating wide habitats where marine life flourished. Ocean temperatures were relatively stable, sea levels were high. Life had settled into familiar patterns that had endured for millions of years. Then, almost imperceptibly at first, the climate began to cool. This cooling was not abrupt. There was no single tipping point that marked the beginning. Instead, subtle shifts in Earth's position and atmospheric conditions altered how sunlight was distributed across the planet. Over long spans of time, cooler conditions became more persistent, especially near the poles. As temperatures dropped, ice began to accumulate. Large ice sheets formed over parts of the southern continent, which at the time was positioned closer to the South Pole. These growing glaciers locked away vast amounts of water, and as more water became frozen on land, sea levels began to fall. This change in sea level was one of the most important factors in the Ordovician-Silurian extinction. Shallow seas are among the richest marine environments. They are warm, sunlit, and full of nutrients. Many early ecosystems depended on these continental shelves. When sea levels fell, these habitats did not shift gently downward. They disappeared. Entire stretches of sea floor that had once supported thriving communities were exposed or drained. For organisms anchored in place, there was no simple way to relocate. Reefs became stranded. Filter feeders lost access to currents. Food webs unravelled not because of a sudden shock, but because the spaces that sustained them slowly vanished. At the same time, cooling temperatures altered ocean circulation. Colder water holds more oxygen, but the changing patterns of mixing created uneven distributions. Some regions became oxygen-rich, while others grew depleted. Species adapted to narrow conditions found themselves increasingly out of place. None of this happened quickly. From the perspective of a single organism, the changes would have been almost unnoticeable. A slightly cooler current, a shoreline creeping outward over generations, a familiar species becoming less common, replaced by another that tolerated the new conditions a little better. Yet across the planet these small changes accumulated. Fossils from this interval show a steady decline rather than an abrupt disappearance. Groups that had been abundant for millions of years gradually became rare. Others vanished entirely from certain regions before disappearing altogether. The extinction unfolded in phases, tracking the advance and retreat of ice and the rise and fall of sea levels. Interestingly, the story does not end with cold alone. As the glaciation reached its peak, conditions began to shift once more. Ice eventually melted. Sea levels rose again. Warmer temperatures returned to many regions, but the damage had already been done. Ecosystems that had been disrupted did not simply return to their previous states. Many species had already been lost during the cooling phase, and others struggled during the transition back. This pattern highlights an important feature of mass extinctions. They are not always caused by a single stress, but by sequences of change. Cooling followed by warming, sea level fall followed by rise, stability broken not once but repeatedly. For marine life, these swings were especially challenging. Organisms adapted to stable conditions found themselves continually adjusting, often without enough time or flexibility to keep up. Those with narrow tolerances declined. Those with broader tolerances quietly persisted. Survival during this extinction was rarely dramatic. There were no heroic adaptations or sudden bursts of innovation. Instead, survival often belonged to species that already happened to be suited to the new conditions. Small organisms with simple needs, creatures capable of living in deeper waters less affected by sea level changes, species with wide geographic ranges that allowed some populations to endure even as others disappeared. Many of the survivors left little impression at the time. They did not dominate ecosystems or immediately diversify. They simply remained, maintaining low populations until conditions stabilized enough for life to expand again. This quiet endurance is easy to overlook when focusing only on what was lost. Yet it is central to understanding how life continues through periods of stress. Extinction removes options. Survival preserves potential. From a geological perspective, the Ordovician Silurian extinction appears as a clear boundary. Below it, fossil-rich layers record diverse marine communities. Above it, those communities look simpler and more uniform. The change is visible, but it's not sharp enough to suggest a single moment of collapse. It reflects a drawn-out process shaped by climate, ice, and water. Importantly, life did not vanish from the oceans. Although a significant portion of marine species disappeared, many groups endured. Some brachiopods survived. Certain trilobite lineages persisted. Early fish-like organisms continued to move through the water. The foundation of marine ecosystems remained intact, even if much of their complexity had been stripped away. In the aftermath, recovery was slow. Ecosystems rebuilt over millions of years, not by returning to what they had been, but by reorganizing around what remained. New species eventually filled empty spaces. Food webs regained complexity. Balance returned, though it looked different than before. This extinction also serves as a reminder that mass extinctions are not always driven by heat, fire, or obvious violence. Cold can be just as disruptive. Gradual environmental shifts can be as powerful as sudden ones. Life often struggles most when change is relentless rather than abrupt. Perhaps the most striking lesson from this first great loss is how quietly it unfolded. There was no single moment when life recognized that it was living through a mass extinction. Each generation experienced only small differences from the last. Slightly altered coastlines, slightly cooler waters, slightly fewer familiar neighbours. Only when viewed across deep time does the full pattern emerge. The Ordovician Silurian extinction marks the first time the fossil record clearly shows life push beyond its usual limits on a global scale. It demonstrates that even stable, long-lived ecosystems can become vulnerable when planetary conditions drift far enough from what they are adapted to. And it shows that survival does not always announce itself. Often it happens quietly, through persistence rather than transformation, through endurance rather than innovation, through life continuing, even as the world it once knew slowly slips away. When the cooling eased and the ice retreated, the oceans did not suddenly return to what they'd been before. There was no moment of relief, no clear signal that the crisis had passed. Instead, recovery unfolded slowly, in fits and starts, across spans of time that stretch far beyond ordinary intuition. Sea levels began to rise as glaciers melted, flooding continental shelves once more. Shallow marine habitats gradually reappeared, bringing light back to regions that had been dry or cold for thousands of generations. Warmer conditions returned to many parts of the ocean, and circulation patterns adjusted again. From a physical perspective, the stage for recovery was set, but life did not rush in to fill it. The aftermath of a mass extinction is often quieter than the extinction itself. Ecosystems do not rebuild all at once. They recover unevenly, shaped by chance, geography, and the traits of the organisms that happen to survive. Some regions stabilize sooner, others lag behind for millions of years. Even when conditions improve, the living world may take a long time to respond. One reason for this slow pace is that extinction does not simply remove species, it removes relationships. Food webs are disrupted, predators lose prey, grazers lose food sources, reef builders disappear, taking shelter with them. Even if individual species survive, the networks that once connected them may be fractured beyond easy repair. Rebuilding those connections requires not just survival, but time. Importantly, extinction does not leave behind an empty world. It clears space. Habitats remain. Resources persist. Light still reaches shallow waters. Nutrients continue to circulate. What is missing is not opportunity, but occupants. This distinction matters because it helps explain why recovery often involves expansion rather than invention. Many surviving species simply spread into roles that were once occupied by others. After the Ordovician Silurian extinction, marine ecosystems slowly reorganized around the survivors. Some groups that had been minor players before became more prominent, not because they had suddenly improved, but because competition had eased. With fewer neighbours drawing on the same resources, surviving organisms could occupy broader ranges and grow more abundant. This process was not predictable. In some regions, recovery progressed relatively quickly. Shelled organisms diversified. Reef-like structures reappeared, though often built by different species than before. In other areas, conditions remained unstable, delaying recovery for extended periods. The fossil record shows patchwork patterns rather than a smooth global rebound. This unevenness is a recurring feature of post-extinction worlds. Recovery depends on local conditions as much as global ones. Temperature, water depth, oxygen levels, and nutrient availability all play roles. So does geography. Isolated basins may recover differently from open oceans. Shallow seas behave differently from deeper environments. Chance also matters more than might be expected. Which species happen to survive in a given region could shape the future of that ecosystem for millions of years. A lineage that endured by coincidence rather than superiority might later diversify simply because it was present at the right place and time. In this way, mass extinctions can redirect evolution without favouring any particular outcome. Early resilience strategies often appear modest rather than dramatic. Many survivors shared traits that made them less sensitive to environmental change. Broad diets allowed flexibility when food sources shifted. Simple body plans required fewer resources to maintain. Wide geographic ranges meant that even if some populations disappeared, others endured elsewhere. Some organisms tolerated low oxygen conditions better than others. Some reproduced quickly, allowing populations to rebound when conditions improved. Others could survive in deeper or cooler waters, avoiding the most extreme changes in shallow seas. None of these traits guaranteed success, but together they increase the odds of persistence. It is tempting to imagine recovery as a return to complexity, but early stages are often marked by simplicity. Post-extinction ecosystems tend to have fewer species, shorter food chains, and less specialized roles. This simplicity is not a failure. It reflects a system rebuilding from a reduced starting point. Over time, interactions become more intricate as diversity increases and niches multiply. In the case of the Ordovician Silurian recovery, life eventually regained much of its former richness. New species emerged, communities became more structured, marine ecosystems once again supported a wide range of forms, yet they were not identical to what had existed before. The composition had shifted, some groups never returned, others took on new importance. This gradual transformation highlights a key principle of recovery. Ecosystems do not rewind. They move forward from altered conditions. The past leaves constraints as well as opportunities. Lost lineages remove possibilities permanently. Surviving ones shape what comes next, often in unexpected ways. Over millions of years, these small differences accumulate, giving rise to worlds that would have been unlikely without the disruption that preceded them. From a human perspective, this pace can feel almost impossibly slow. From a geological perspective, it is simply how life operates. Recovery measured in millions of years is not hesitation, it is normal. The fossil record preserves this patience. Layer by layer it shows diversity creeping back, new forms appearing, then spreading, old patterns giving way to new arrangements. There is no single marker that announces recovery is complete. Instead, stability returns gradually, almost quietly. Gentle humour sometimes arises from this contrast. After one of the planet's most significant losses, life responds not with urgency, but with persistence. There is no rush, no grand redesign, just organisms doing what they can, where they can, with what remains available. This measured response is part of why life has endured repeated crises. Rapid change often overwhelms complex systems. Slow rebuilding allows adjustments to settle and interactions to stabilize. Over time, resilience emerges not from speed but from accumulation. The recovery following the first mass extinction set a pattern that would repeat again and again in Earth's history. Loss creates space. Space invites expansion. Expansion leads to new relationships. Those relationships gradually restore complexity, though never in quite the same form. Seen through this lens, extinction and recovery are not opposites. They are linked phases of a longer process. One removes possibilities, the other explores what remains. By the end of this long recovery, marine life once again filled the seas with movement and interaction. The ocean supported diverse communities, adapted to the new conditions shaped by climate, geography, and history. Balance returned not as a restoration of the past, but as a new arrangement built from survival. Life had endured its first great test, not by resisting change, but by absorbing it, by spreading into newly available spaces, by rebuilding patiently, one generation at a time. The planet had demonstrated something important. Even after widespread loss, life does not start over. It continues, reshaped, carrying the imprint of what was lost into whatever comes next. The late Devonian extinction unfolded differently from the one before it. There was no clear beginning, no single environmental shift that could be pointed to as the cause. Instead, it arrived in stages, stretched across a long span of time, shaped by a web of changes that slowly altered the chemistry of the oceans and the balance of life within them. By the Devonian period, marine ecosystems had recovered much of their complexity. Reefs were extensive and diverse, built by organisms that formed large, stable structures across shallow seas. Fish had diversified into a wide range of forms, experimenting with jaws, armour, and movement. Food webs were layered and intricate, with predators, grazers, and filter feeders woven into long-established relationships. At the same time, the planet was changing in a quieter but deeply significant way. For the first time, plants were spreading widely across land. Early forests began to take hold along riverbanks and floodplains. Roots pushed into soil, breaking down rock and stabilizing sediments. Leaves reached upward, capturing sunlight and exchanging gases with the atmosphere. From the perspective of life on land, this was an extraordinary expansion. From the perspective of the oceans, it was a slow complication. As plants altered the land, they also changed what flowed into the sea. Roots increased the rate at which rocks weathered, releasing nutrients into rivers. These nutrients were carried downstream and eventually washed into coastal waters. In moderation, such inputs can support life. In excess, they can destabilize it. Over long periods, nutrient-rich runoff encouraged the growth of microscopic organisms in the oceans. These blooms increased biological activity near the surface. When those organisms died, they sank, and their decomposition consumed oxygen from deeper waters. Slowly, in many regions, oxygen levels declined. This process did not empty the oceans of oxygen entirely. Instead, it created layers. Surface waters could remain relatively rich, while deeper zones became depleted. These low-oxygen regions expanded and contracted over time, sometimes retreating, sometimes spreading across large areas. Marine life responded unevenly. Organisms that required well-oxygenated water struggled as suitable habitats shrank. Reef builders were especially vulnerable. Their complex structures depended on stable conditions, clear water, and consistent chemistry. As oxygen levels fluctuated and nutrients increased, reefs began to weaken. Growth slowed, mortality increased, entire reef systems gradually declined. Other groups proved more tolerant. Some fish adapted to lower oxygen conditions. Certain invertebrates survived in environments that would have been uninhabitable earlier. These survivors did not necessarily thrive, but they persisted, maintaining a foothold as conditions changed. What makes the late Devonian extinction distinctive is how prolonged it was. Rather than a single pulse of loss, the fossil record shows multiple declines separated by partial recoveries. Some species disappeared, while others temporarily rebounded. Stress eased in some regions, only to return later. This pattern suggests that environmental pressures came and went, never quite allowing ecosystems to settle into a new stable state. Ocean chemistry played a central role in this instability. Changes in carbon cycling, nutrient availability, and oxygen distribution interacted in complex ways. Volcanic activity may have contributed additional gases to the atmosphere. Climate shifts altered ocean circulation. Each factor influenced the others, creating feedback loops that were difficult to escape. It would be misleading to assign blame to any single cause. The spread of land plants, for example, was not a destructive force in itself. On the contrary, it laid the groundwork for future terrestrial ecosystems and eventually transformed the planet into a greener, more diverse world. The challenges it posed to marine life were unintended consequences of a larger transformation, not evidence of a mistake or failure. In this sense, the late Devonian extinction reflects complexity rather than catastrophe. Multiple processes overlapped. Each change nudged ecosystems closer to their limits. Together, they created conditions that many species could not tolerate indefinitely. From the perspective of individual organisms, the experience would have been gradual. A reef might grow more slowly from one generation to the next. Fish populations might thin slightly. Certain species might become harder to find, while others became more common. No single moment would have felt decisive. Yet across millions of years, these small shifts accumulated into widespread loss. Fossil evidence supports this drawn-out timeline. Species vanish from some layers, reappear in others, then disappear entirely later on. Diversity declines unevenly across different groups. The extinction did not strike everywhere at once, nor did it affect all forms of life equally. Survival during this period once again favoured flexibility. Organisms with broad tolerances, adaptable feeding strategies, or the ability to occupy a range of habitats were more likely to endure. Simpler forms often outlasted more specialised ones. Mobility helped in some cases, allowing species to move away from unfavourable conditions, though even this was not a guarantee. As reef ecosystems collapsed, the spaces they left behind were not immediately refilled. Complex structures take time to rebuild, and the environmental conditions that had supported them were no longer reliable. The loss of reefs removed important habitats, further amplifying the effects of oxygen decline and chemical instability. Gentle humour can be found in the patience of the process. Life did not respond to worsening conditions with sudden innovation or dramatic reinvention. It simply continued, adjusting where it could, enduring where adjustment was impossible, and slowly shedding forms that could no longer persist. By the end of the late Devonian, marine ecosystems looked noticeably different. The great reef systems that had once dominated shallow seas were largely gone. Fish diversity had been reshaped. Many familiar groups had declined or vanished, while others remained to carry life forward. Yet, as before, life itself was not extinguished. The ocean still contained a wide array of organisms. Food webs continued, albeit in altered forms. The foundations of future ecosystems remained intact, even if their architecture had been simplified. The late Devonian extinction stands as an example of how gradual environmental change can be just as disruptive as sudden events. It shows how interconnected Earth's systems are, with changes on land influencing life in the sea, and how long-lasting the consequences of those interactions can be. Rather than a single disaster, it was a long period of adjustment gone too far, a reminder that ecosystems can absorb stress up to a point, but that persistent pressure, even when subtle, can reshape life on a planetary scale. In the end, this extinction did not signal failure, but transition. It closed one chapter of Earth's marine history and quietly prepared the conditions for what would follow, carrying forward the survivors into a world that would never quite look the same again. After the long strain of the late Devonian losses, life did not rush to replace what had vanished. There was no sudden return to former complexity. No clear winners stepping neatly into the spaces left behind. Instead, the living world entered a period of experimentation, marked by tentative steps, uneven progress, and a surprising amount of quiet creativity. This phase of recovery shows something important about how evolution works under pressure. When established systems collapse, dominance becomes less useful than adaptability. The traits that once ensured success may no longer fit the new conditions. In their place, flexibility, tolerance, and simplicity often take the lead. In the oceans, the disappearance of large reef systems opened vast areas of seafloor. These spaces were not empty in a physical sense. Light still reached shallow waters. Nutrients continued to circulate. What was missing were the familiar structures that had once organized life around them. With those frameworks gone, new arrangements became possible. Some organisms expanded into roles they had never occupied before. Others diversified into multiple forms, each testing a slightly different way of living. Small variations in feeding, movement, or reproduction could now make a difference, not because they were superior, but because competition was reduced. This is one of the quieter effects of extinction. When many species disappear, the remaining ones face fewer constraints. They are not suddenly better suited to the environment. They are simply less crowded. That freedom allows variation to matter again. Fish provide a clear example of this process. After the Devonian losses reshaped marine ecosystems, surviving fish lineages began to explore new body plans and behaviours. Some developed stronger jaws, others became more efficient swimmers, some remained small and adaptable, while others slowly increased in size. None of these paths was guaranteed to succeed. Many led nowhere. A few persisted. Nature, it turns out, is comfortable with trying many things at once. This trial and error approach is not driven by foresight or intention. There is no plan to rebuild complexity or restore balance. Variation arises naturally through reproduction. Environments apply pressure. Forms that happen to fit those conditions continue, while others fade away. Over time, this process gives the appearance of direction, even though it unfolds without guidance. Gentle humour can be found in how inefficient this method is. Evolution does not test one idea at a time. It tries everything, everywhere, all at once, and keeps whatever happens to work well enough. Many experiments fail quietly, leaving little trace beyond a few fossils embedded in rock. Diversity can increase after collapse precisely because the rules are less rigid. Before an extinction, ecosystems are often tightly packed. Niches are filled. Competition is intense. Small differences offer little advantage. After widespread loss, those constraints loosen. New niches appear, not because the environment created them deliberately, but because previous occupants are gone. As surviving species spread into these spaces, populations fragment. Isolated groups adapt to local conditions. Over long periods, these differences can accumulate into new species. What begins as a modest expansion can, given enough time, lead to renewed diversity. This process is slow, and it rarely restores what was lost. Post-Devonian ecosystems did not recreate the vast reef systems of earlier times right away. Instead, they developed different structures, often simpler and more flexible. Rather than towering, complex habitats, many environments were organized around mobile organisms and loosely connected food webs. This shift reflects a broader pattern in post-extinction worlds. Stability returns gradually, but complexity builds cautiously. Systems that rely on precise conditions tend to reappear only after environments have remained stable for long stretches of time. Until then, adaptability is favored over specialization. Plants on land continue to evolve during this period as well. Early forests expanded and diversified, reshaping soils and atmospheric conditions. While these changes had contributed to earlier stress in the oceans, they also laid the groundwork for future resilience. Over time, plant life would help regulate climate and stabilize landscapes, though that balance was still far from settled. In both marine and terrestrial environments, recovery involved many false starts. Some groups diversified briefly, only to decline again when conditions shifted. Others remained rare for millions of years before finally expanding. The fossil record preserves these fluctuations as uneven patterns, with bursts of appearance followed by long stretches of relative quiet. Importantly, dominance was not the goal. The species that persisted were not necessarily the most imposing or complex. Often, they were the ones that asked the least of their environment. Modest energy needs, flexible diets, and broad tolerances proved more useful than size or strength. In uncertain worlds, being adaptable mattered more than being impressive. This principle appears again and again in Earth's history. After disruption, life does not rush toward grandeur. It moves cautiously, spreading risk across many forms rather than investing heavily in a few. Complexity returns later, once conditions have proven reliable. From a human perspective, this can feel anticlimactic. After major loss, one might expect dramatic innovation or sudden leaps forward. Instead, recovery looks understated. Small changes, gradual expansion, long periods where very little seems to happen. Yet this understated phase is where resilience is built. By testing many forms quietly and over long spans of time, life increases the chances that some lineages will endure future changes. Diversity becomes a kind of insurance, not because every form is necessary, but because variety increases the likelihood that something will cope when conditions shift again. The Devonian aftermath shows this clearly. While many ancient groups never returned, the survivors carried forward a wider range of possibilities. The living world became less dependent on a single, dominant structure or strategy. In this sense, collapse led not to weakness, but to a more distributed form of resilience. There is no neat dividing line between recovery and normal evolution. Adaptation does not begin only after crisis. It continues constantly, adjusting to subtle pressures and opportunities. What changes after an extinction is the scale of possibility. With fewer constraints, evolution explores more freely. Over millions of years, these explorations accumulate. New ecosystems take shape. Food webs grow longer. Interactions become more specialized. What once seemed like a simplified world gradually develops its own complexity, different from what existed before, yet equally intricate. Life learning to adapt after the Devonian losses was not a moment of triumph. It was a quiet, persistent process, one that relied on patience rather than brilliance, on endurance rather than conquest. In the end, this period reminds us that survival is not about winning. It is about continuing, about fitting into changing conditions without needing to dominate them, about allowing variation to unfold, even when many paths lead nowhere. Through this slow experimentation, life prepared itself, unknowingly, for the challenges still ahead. The world it was rebuilding would face new stresses, new shifts, and new tests, but it would do so with a broader foundation, shaped by the lessons of loss and the quiet power of adaptation. The Permian Triassic extinction marks the most extensive loss of life preserved in the fossil record. Yet despite its scale, it did not arrive as a sudden catastrophe. There was no single instant when the world changed overnight. Instead, the planet entered a prolonged period of strain, during which environmental pressures accumulated slowly and relentlessly, testing life in ways it had never experienced before. By the late Permian period, life on Earth had achieved remarkable diversity. Forests covered large areas of land. Insects had spread widely. reptile-like animals occupied a range of ecological roles. In the oceans, complex food webs supported reefs, fish, and countless invertebrates. Ecosystems were intricate, interconnected, and productive. That complexity, however, came with a cost. Highly developed systems often depend on stable conditions. Temperature ranges, oxygen levels, and chemical balances need to remain within familiar limits. When those limits are pushed for too long, even resilient ecosystems can begin to falter. During this time, one of the most significant geological events in Earth's history was unfolding. In what is now Siberia, vast volcanic eruptions began and continued for an extended period. These eruptions were not brief outbursts. They persisted for hundreds of thousands of years, releasing enormous volumes of lava and gases into the atmosphere. The immediate landscape around these eruptions was transformed, but the wider effect spread far beyond the eruption sites. Volcanic gases altered atmospheric composition, gradually increasing temperatures across the planet. Warming was not uniform, nor was it gentle. It arrived in pulses, intensifying stress on both land and sea. As temperatures rose, other systems began to respond. Warmer oceans hold less oxygen. Circulation patterns changed, reducing the mixing that normally brings oxygen-rich water to deeper regions. Large portions of the seafloor became low in oxygen, or in some areas nearly depleted. Marine organisms that relied on consistent oxygen levels found their habitable zones shrinking. On land, rising temperatures increased evaporation and altered rainfall patterns. Some regions became drier, others experienced more extreme swings between wet and dry conditions. Plants struggled to maintain stable growth, and soils degraded. Food chains that depended on predictable plant productivity became less reliable. Crucially, these changes did not occur all at once. The Permian Triassic extinction unfolded as a long period of environmental stress. Conditions worsened, eased slightly, then worsened again. Each phase removed a portion of life that could not tolerate the new limits. Over time, these losses accumulated into widespread extinction. In the oceans, reef ecosystems collapsed almost entirely. The complex structures that had supported diverse communities for millions of years disappeared. With them went countless species that depended on those habitats. Shelled organisms declined sharply. Many fish lineages vanished. Food webs shortened and simplified. On land, many dominant animal groups declined or disappeared. Large specialized species were particularly vulnerable. High energy demands and narrow tolerances made survival difficult when conditions fluctuated unpredictably. Forests thinned. Insects declined in diversity. Entire ecological roles were lost. Despite this scale of loss, it is important to resist dramatic framing. The planet did not burn overnight. Life did not vanish in a single wave. Instead, Earth became gradually less hospitable. Each change nudged ecosystems closer to their limits until, for many species, those limits were crossed. Survival during this time depended less on strength or dominance and more on flexibility. Organisms with modest needs fared better. Simple body plans required fewer resources to maintain. Broad diets allowed adjustment when food sources shifted. The ability to tolerate low oxygen or variable temperatures became more valuable than specialized adaptations suited to stable environments. In the oceans, some small, opportunistic species persisted in conditions that would have been lethal to more complex organisms. Certain microbes and invertebrates endured in low-oxygen waters, maintaining basic food chains even as diversity collapsed. These survivors were not thriving in the usual sense, but they remained present. On land, smaller animals with flexible lifestyles were more likely to persist. Burrowing offered protection from temperature extremes. Generalist feeding strategies reduced dependence on any single food source. Reproduction at smaller body sizes required fewer resources and allowed populations to recover more quickly when conditions briefly improved. Gentle humour emerges, if anywhere, in the contrast between expectation and outcome. After millions of years of evolutionary refinement, success belonged not to the most advanced or impressive forms, but to those content with simplicity. Nature, it seems, rewarded restraint over ambition during this period. The fossil record from the Permian-Triassic boundary reflects this drawn-out collapse. Species disappear in stages. Diversity declines unevenly across different groups and regions. Some ecosystems linger in degraded forms before finally giving way. Others collapse earlier and more completely. Chemical evidence preserved in rock supports this picture of prolonged stress. Shifts in carbon and oxygen markers indicate repeated disruptions to global cycles. These signals align with periods of intense volcanic activity, reinforcing the idea that long-term environmental pressure, rather than sudden disaster, drove the extinction. Even after the most severe phase passed, conditions did not immediately improve. The early Triassic period that followed was marked by continued instability. Temperatures remained high. Oxygen levels were slow to recover. Ecosystems struggled to regain complexity. Recovery was delayed not because life had lost the ability to adapt, but because the environment itself remained challenging. This extended aftermath underscores how deeply the Permian-Triassic extinction reshaped the planet. It was not simply an event that ended and moved on. It altered baseline conditions for millions of years, influencing what kinds of life could exist and how ecosystems functioned. Yet even here, life did not disappear entirely. Basic food webs persisted. Small populations endured. Evolution did not pause. It adjusted to the new limits, exploring forms that could cope with heat, low oxygen, and instability. These survivors would become the foundation for later recovery, though at the time they likely appeared unremarkable. Seen through deep time, the Permian-Triassic extinction represents a narrowing of possibilities. Many evolutionary paths ended. Others continued, not because they were superior, but because they were compatible with harsh conditions. This narrowing had long-lasting consequences. Future ecosystems would be built from a reduced set of survivors, shaping the direction of life for the remainder of Earth's history. Entire groups that once dominated would never return. Others would rise to prominence only because competitors were gone. The scale of loss makes this extinction stand apart, but its underlying lesson remains consistent with earlier events. Long-term environmental stress can be more disruptive than sudden shocks. Stability matters. When it erodes over extended periods, even robust systems can unravel. Perhaps the most striking aspect of the Permian-Triassic extinction is how quietly it teaches this lesson. There is no single dramatic image that captures it fully, no singular moment to point to. Instead, it is remembered through absences, through simplified ecosystems, and through the long delay before recovery truly began. Life endured not by resisting change, but by fitting within narrower bounds, by lowering its demands, by persisting in modest forms until conditions allowed greater complexity once again. In this way, the largest extinction in Earth's history is also a story of endurance through constraint, of survival achieved not through dominance, but through flexibility and patience, and of a planet that, under sustained pressure, reshaped the living world in ways that would echo far into the future. When the most severe phase of the Permian-Triassic extinction finally eased, the planet did not rebound with relief. There was no sudden return of forests, reefs, or complex food webs. Instead, Earth entered what would become the longest and most difficult recovery in its history, a slow climb out of instability that tested life's patience as much as its resilience. The early Triassic world was a challenging place to inhabit. temperatures remained high for extended periods. Ocean circulation was sluggish. Oxygen levels, particularly in marine environments, stayed uneven and often low. On land, soils were poor and vegetation sparse in many regions. The basic conditions that support stable ecosystems were still unreliable. For life, this meant that survival continued to require compromise. Ecosystems rely on predictability. Seasonal patterns, steady nutrient cycles, and consistent temperatures allow complex relationships to form and persist. After the Permian losses, those patterns were difficult to establish. Just as communities began to stabilize, conditions would shift again, undoing fragile progress. This instability slowed recovery dramatically. In the oceans, reef systems were almost entirely absent for millions of years. Without reefs, many organisms lost essential habitats. Food webs remained short and simplified. Predators were limited in size and number. The variety of life was reduced, not because evolution had stalled, but because the environment could not yet support greater complexity. On land, forests struggled to return. Large trees take time to establish, and they require relatively stable climates. In the early Triassic, extreme heat and irregular rainfall made long-term growth difficult. Instead of dense forests, many regions were dominated by hardy, fast-growing plants that could tolerate poor conditions but offered limited ecological structure. This meant fewer niches for animals. With limited plant diversity and unstable food sources, animal communities remained sparse. Many surviving species stayed small. Large-bodied animals were rare, as high-energy demands were difficult to meet. Even those that persisted often occupied narrow ecological roles, carefully balanced against the constraints of their environment. What makes this recovery stand out is not just its length, but its unevenness. Some regions showed signs of improvement earlier than others. Local ecosystems would briefly become more diverse, only to decline again when conditions shifted. These starts and stops are recorded in the fossil record as irregular patterns of appearance and disappearance, reflecting a world still struggling to find balance. Chemical evidence reinforces this picture. Fluctuations in carbon and oxygen indicators suggest that global cycles remained unsettled for a long time. Volcanic activity did not end abruptly, and its lingering effects continue to influence climate and ocean chemistry. Recovery was not delayed by a lack of survivors, but by a lack of stable conditions. Patience becomes a central theme here. From a human perspective, millions of years seems unimaginably long. From the planet's perspective, it is simply the pace at which deep recovery occurs after profound disruption. Earth does not hurry to restore complexity. It allows conditions to stabilize first, then gradually permits life to rebuild. Life, in turn, adapts to this pace. During the long recovery, evolution favored organisms that could tolerate uncertainty. Generalists thrived where specialists struggled. Species with flexible diets, rapid reproduction, and broad environmental tolerances were more likely to persist. This was not a time for elaborate strategies. It was a time for reliability. Gentle humour can be found in the contrast between expectation and reality. After the largest extinction in Earth's history, one might expect dramatic innovation or rapid diversification. Instead, life took its time, as if carefully testing each step before committing to the next. The planet, it seems, prefers caution over enthusiasm after a crisis. Eventually, signs of progress became more consistent. Marine ecosystems began to show increased diversity. New reef builders appeared, different from those that had been lost. Food webs slowly lengthened. On land, forests expanded more reliably as climates moderated and soils improved. Insects diversified. Animal communities became more complex. These changes did not happen everywhere at once. Recovery remained patchy, shaped by geography and local conditions. Some areas became refuges of stability, supporting more advanced ecosystems earlier. Others lagged behind, constrained by lingering heat or chemical imbalance. Over time, however, these pockets of stability expanded and connected. An important lesson emerges from this drawn-out process. Recovery does not mean returning to what existed before. The post-Permian world was fundamentally different. New dominant groups emerged. Old ones were gone forever. Ecosystems were rebuilt from a smaller set of survivors, leading to new arrangements and new directions in evolution. This rebuilding required time not because life was weak, but because complexity itself is delicate. Complex systems depend on many interacting parts. Reassembling those interactions after widespread loss is slow work. Each new relationship must prove stable under existing conditions. Each increase in diversity raises new challenges as well as new possibilities. Seen this way, the long recovery becomes a measure of care rather than delay. Life returned, but it did so cautiously. It waited for the planet to become more predictable. It explored new forms slowly, allowing successful strategies to spread before adding further complexity. This gradual approach reduced the risk of collapse in a still uncertain world. The fossil record reflects this patience clearly. Diversity increases step by step. Large gaps between major changes are filled with long periods of relative calm. There is no sudden explosion of life, but a steady accumulation of forms and interactions. Eventually, ecosystems reached a new level of stability. Forests covered much of the land again. Oceans supported diverse communities. Food webs became layered and resilient. Life once more occupied a wide range of environments, though in configurations shaped by the long recovery. The Permian recovery reminds us that extinction is not the end-of-life story. It is a severe interruption. What follows is not immediate renewal, but gradual rebuilding. Loss clears space, but filling that space requires time, stability, and patience. Earth's history shows this pattern repeatedly. After even the deepest crises, life returns, not quickly, not dramatically, but reliably. In this longest recovery, the planet demonstrated something quietly profound. Given enough time and conditions that slowly improve, life will explore what remains possible. It will rebuild complexity carefully, one interaction at a time. The world that emerged from this recovery was not the world that had been lost. It was something new, shaped by endurance rather than abundance, and it carried forward a lesson that would echo through later extinctions. Life can survive extraordinary loss, but to truly recover it needs time. The Triassic-Jurassic extinction unfolded during a time when the planet itself was being rearranged. Continents that had once been joined together were slowly pulling apart. Vast land masses shifted position. New coastlines formed. Ocean basins widened. This gradual breakup did not happen quietly in environmental terms. It introduced instability into nearly every system life depended on. At the end of the Triassic period, much of the world's land was still connected as a single supercontinent. This arrangement shaped climate in distinctive ways. Large interior regions were far from the moderating influence of oceans, leading to strong seasonal extremes. Some areas experienced long, dry periods. Others were subject to intense rainfall. Life adapted to these patterns over millions of years, settling into ecosystems that could tolerate variability, but still relied on a degree of predictability. As the supercontinent began to fragment, that predictability weakened. The slow pulling apart of land masses opened new pathways for volcanic activity. Along the rifting zones, magma rose and spread across enormous areas. These eruptions were not brief. They occurred repeatedly over long spans of time, releasing gases that altered atmospheric composition and climate. temperatures rose, carbon levels increased, weather patterns became more erratic. Once again, stress accumulated rather than striking suddenly. On land, shifting climates challenged plant communities. Forests adapted to one pattern of rainfall found themselves coping with new extremes. Soils eroded in some regions and accumulated in others. Plant diversity did not collapse outright, but its distribution changed, with knock-on effects for animals that depended on specific vegetation. In the oceans, changes were equally subtle and persistent. As continents separated, ocean circulation patterns shifted. Currents that once transported heat and nutrients efficiently were disrupted. Some regions warmed significantly, others cooled. Oxygen distribution changed, affecting marine life that depended on stable conditions. What makes the Triassic-Jurassic extinction distinctive is that it did not dramatically reduce overall diversity in the same way earlier extinctions had. Instead, it reshaped which groups held dominant roles within ecosystems. Many animal lineages declined or disappeared, particularly large, specialized forms that required stable environments. On land, several groups of reptiles that had once been prominent faded from the fossil record. In the seas, certain marine reptiles and invertebrates declined as conditions shifted, yet life as a whole continued. A wide range of species persisted through this interval. Food webs remained functional. Ecosystems did not simplify to the extreme degree seen after the Permian extinction. What changed most was the balance of influence. Some groups became less common, others, previously minor components of ecosystems, found themselves better suited to the new conditions. Among these were the early dinosaurs. It is important to approach their emergence without drama. Dinosaurs did not suddenly take over the world. They did not arrive as conquerors sweeping aside competitors. For much of the Triassic, they were small, relatively rare animals, living alongside many other reptile groups that were just as successful, if not more so. What distinguished early dinosaurs was not superiority, but compatibility. Many dinosaurs had upright postures and efficient movement, which may have helped them cope with changing environments. Some were adaptable in diet, others reproduced efficiently. These traits did not guarantee dominance, but they increased the likelihood of persistence as conditions fluctuated. As environmental stress continued and other groups declined, dinosaurs remained. They did not thrive immediately, they simply endured. This pattern repeats throughout Earth's history. Groups that later appear dominant often begin as survivors rather than winners. Their eventual prominence reflects the removal of competitors as much as their own abilities. The Triassic-Jurassic extinction illustrates this clearly. When certain large reptile groups disappeared, ecological roles opened. Predatory niches became available. Herbivore communities shifted. Dinosaurs expanded into these spaces gradually, not because they had planned to, but because they were present when opportunities arose. In the oceans, a similar reshuffling occurred. Some marine reptiles declined, others persisted and diversified later. Fish continued to adapt and spread. Marine ecosystems remained complex, though their composition shifted in response to changing conditions. This extinction also highlights how dominance can change without a dramatic loss of diversity. Many species survived, but the structure of ecosystems altered. Which organisms were most common? Which filled key roles? Which set the tone for interactions? These shifts can have long-lasting effects, steering the course of evolution even when overall numbers remain relatively stable. Environmental instability played a central role in driving these changes. Repeated volcanic episodes injected gases into the atmosphere, leading to warming and acidification. Climate fluctuations stressed organisms adapted to narrow conditions. Habitats shifted repeatedly. favouring those with flexibility over those specialised for consistency. As before, these pressures unfolded over long periods. There was no single boundary that marked the extinction cleanly. Fossil records show declines occurring at different times in different places. Some groups disappeared earlier, others lingered into the earliest part of the Jurassic before finally fading away. Survival during this interval once again depended on modest traits: small to medium body size reduced energy demands. Broad diets allowed animals to adjust as plant communities changed. Geographic range mattered. Species spread across large areas were more likely to find refuges when local conditions deteriorated. Gentle humour can be found in how unspectacular this survival often was. The ancestors of animals that would later dominate the planet spent long stretches simply avoiding trouble, living in the ecological background rather than at the centre of attention. By the time the Jurassic period was fully underway, the reshuffling had become clearer. Dinosaurs were more common and more diverse. They occupied a range of ecological roles, from small agile predators to large herbivores. Other reptile groups were reduced or gone, not because dinosaurs defeated them directly, but because changing conditions favoured different combinations of traits. This distinction matters. Framing extinctions as competitions between groups can obscure the underlying processes. Environmental change sets the stage. Survival depends on compatibility with new conditions. Dominance emerges as a consequence, not a goal. The Triassic-Jurassic extinction serves as a reminder that evolutionary success is often temporary and context-dependent. The traits that allow persistence in one environment may offer little advantage in another. Groups that seem ascendant can fade quietly when conditions shift again. In the aftermath of this extinction, ecosystems continued to function and diversify. Life did not need to rebuild from near collapse as it had after the Permian. Instead, it reorganised around a new balance of influence. The world moved forward with a different cast of common characters. From a distance, this extinction appears less dramatic than others. There is no single overwhelming loss that defines it. Its significance lies in how it redirected the course of life, shaping which groups would define the next era. Early dinosaurs did not inherit the planet through conquest. They remained because they endured. Their rise was a side effect of long-term environmental instability and the quiet disappearance of others. The Triassic-Jurassic extinction reminds us that change in the living world often happens without fanfare. Dominance can shift gradually. New patterns can emerge from persistence rather than power. Life continued, adaptable and patient, moving forward through a world still in motion. After each great upheaval, the world that follows is never simply a repaired version of what came before. Ecosystems reorganize, sometimes subtly, sometimes profoundly, guided by new conditions and shaped by whatever life happens to remain. The rules are not rewritten deliberately. They change because the environment has changed, and life adjusts in response. In the wake of extinction, familiar structures often disappear. Long-standing food webs are disrupted. Habitats lose their defining features. What emerges instead is a landscape of possibility mixed with constraint. Some niches are suddenly open. Others no longer exist at all. Survival in this context does not reward past success. It depends on how well organisms fit the present moment. This is one of the reasons extinction reshapes ecosystems so thoroughly. It does not simply remove species, it alters the relationships that define how life functions. Predators may find themselves without prey. Grazers may lose the plants they depend on. Shelter, once abundant, may become scarce. Even when individual species survive, the world they inhabit may no longer resemble the one they evolved within. As ecosystems reorganize, new patterns form, often in unexpected ways. Some organisms expand rapidly into newly available spaces. Others remain limited, constrained by lingering instability. A species that becomes common after an extinction is not necessarily better designed or more advanced. It may simply be present at the right place, at the right time, with traits that happen to work under the new conditions. This distinction is important. Survival does not imply superiority. It can be tempting to view the fossil record as a ladder, with life steadily climbing toward greater complexity or refinement. Extinctions disrupt this image. They reveal a history that is uneven, branching, and often guided by chance. Many highly specialized organisms vanish, while simpler ones persist. Later success often rests on endurance rather than excellence. Chance plays a larger role and is often assumed. When environments change rapidly, small differences can have large consequences. A population slightly closer to a refuge may survive while another disappears. A species with a wider range may persist simply because some members happen to live where conditions remain tolerable. These outcomes are not planned. They are the result of circumstances intersecting with biology. Once those survivors remain, they shape what comes next. Their traits influence how ecosystems rebuild. Their interactions determine which niches become established first. Over time, these early arrangements can become entrenched, guiding evolution along particular paths. In this way, chance events during and after extinction can echo through millions of years of history. Adaptation still matters, but it operates within limits set by circumstance. Organisms that endure often share certain qualities: flexibility in diet, tolerance for variable conditions, modest energy demands. These traits increase the odds of survival when environments are unstable. But even the most adaptable species cannot thrive everywhere. Opportunity must exist alongside ability. As ecosystems stabilize, competition returns, niches fill, relationships grow more intricate. What began as a loosely organized community becomes structured once again. Yet the structure is rarely the same as before. New rules emerge, shaped by different players and different constraints. This process can give the impression of progress, but it is not directional in the way that word suggests. Complexity may increase over time, but it does so unevenly. Some periods favor elaborate ecosystems, others favor simplicity. After extinctions, complexity often returns cautiously, built layer by layer rather than all at once. Systems become intricate again, not because life is striving toward an ideal, but because stable conditions allow interactions to accumulate. Gently dismantling the idea of linear progress means recognizing that evolution has no endpoint. There is no preferred destination, no final form toward which life moves. Each moment reflects a balance between what is possible and what is permitted by the environment. When conditions shift, that balance shifts with them. Extinctions highlight this reality clearly. Groups that once dominated can disappear entirely. Others, previously unremarkable, can become central. These changes are not judgments on worth or success. They are outcomes of compatibility with changing circumstances. Gentle humour can be found in how often expectations fail. The fossil record is filled with organisms that seemed perfectly suited to their time, only to vanish when conditions changed slightly. It is also filled with survivors that look ordinary or even awkward, yet persist through upheaval and later flourish. Evolution does not reward elegance or ambition, it rewards adequacy. As new worlds take shape after extinction, ecosystems reflect this pragmatism. Food webs emphasize reliability. Interactions favor resilience over efficiency. Diversity increases not because life is improving, but because stability allows variation to persist. Over long spans of time, these rebuilt systems can become as complex and rich as those that preceded them. But they are not better in any absolute sense. They are simply different, shaped by different histories and constraints. Understanding this helps place humanity's own position in context. The present world feels familiar and stable, yet it is the product of countless reorganizations. Its ecosystems exist not because they are optimal, but because they are the result of what survived and adapted under past conditions. There is nothing inevitable about their form. Extinction teaches that the rules of a life are flexible, but not forgiving. Change opens possibilities, but it also closes them permanently. New worlds emerge, but they are always built from limited materials. After upheaval, life does not climb upward. It spreads outward, exploring what remains available. Some paths flourish, others fade. Over time, patterns settle into something that appears ordered, even though it arose from disruption. In this way, extinction and recovery reveal a living world guided not by progress, but by persistence, by chance encounters and workable solutions, by organisms making do with what the planet allows at any given moment. New worlds follow old ones, each governed by its own rules, not better, not worse, simply shaped by survival, circumstance, and time. The Cretaceous-Paleogene extinction is often remembered as a moment, a single impact, a sudden ending. Yet when viewed through the lens of Earth's longer history, it becomes something quieter and more instructive, less a dramatic instant, and more a turning point shaped by what followed rather than what struck. Near the end of the Cretaceous period, life on Earth was rich and varied. Dinosaurs occupied many ecological roles on land. Forests were widespread. Insects were abundant. In the oceans, complex food webs supported large marine reptiles, diverse fish, and extensive plankton communities. Ecosystems were productive and interconnected, refined over millions of years of relative stability. Then, an asteroid arrived. The impact itself was brief on geological timescales. A collision with immense energy released heat, pressure, and debris. But focusing on that instant can obscure what truly mattered. The lasting effects were environmental, unfolding over years, decades, and longer. Material thrown into the atmosphere spread around the globe. Fine particles and aerosols lingered, reducing the amount of sunlight reaching the surface. Temperatures dropped. Photosynthesis slowed. Food production at the base of many ecosystems declined sharply. This dimming of the planet was not permanent, but it lasted long enough to place severe strain on living systems. In the oceans, plankton populations were particularly affected. These microscopic organisms form the foundation of marine food webs. When their numbers fell, the effects rippled upward. Creatures that fed on plankton struggled. Predators that relied on those creatures followed. Entire chains weakened not because of direct destruction, but because energy flow was interrupted. On land, plants faced similar challenges. Reduced sunlight limited growth. Many species that depended on consistent photosynthesis declined. Herbivores lost food sources. Carnivores, in turn, lost prey. The disruption moved step by step through ecosystems, guided by dependency rather than force. What makes this extinction distinctive is not just the presence of an impact, but how selectively it reshaped life. Not all dinosaurs disappeared. Birds, which are dinosaurs by lineage, survived. Many mammals endured. Crocodilians persisted. Turtles remained. Numerous plants and insects continued as well. The extinction was extensive, but it was not universal. Survival depended less on size or strength, and more on lifestyle. Large animals with high energy demands struggled when food became scarce. Specialized feeders found it difficult to adapt quickly when their preferred resources vanished. Species with narrow ecological roles were less flexible under rapidly changing conditions. In contrast, organisms with modest needs fared better. Small body size reduced energy requirements. Broad diets allowed adjustment when specific food sources declined. Burrowing provided shelter from temperature extremes. Dormant life stages helped some species wait out harsh conditions. These advantages were not dramatic adaptations developed in response to the crisis. They were existing traits that happened to fit the new reality. In this way, survival was largely circumstantial. Mammals, for example, had existed alongside dinosaurs for a long time without dominating ecosystems. They were generally small, adaptable, and often active at times when conditions were less demanding. These traits did not make them superior. They made them compatible with a world temporarily stripped of abundance. Birds, too, benefited from flexibility. Some could fly to find resources. Others fed on a wide range of foods. Their small size and efficient metabolism increased their chances of persistence. Again, survival reflected fit, not victory. In marine environments, certain fish and invertebrates endured while larger marine reptiles disappeared. Plankton communities eventually recovered, though often with different compositions. Food webs reorganised around what remained. The aftermath of the extinction was not immediately welcoming. For a time, ecosystems were simplified. Diversity was reduced. Many ecological roles were empty. Recovery began cautiously, guided by surviving lineages rather than replaced ones. As conditions stabilised, new species emerged, often filling roles that had been left vacant. This recovery did not involve a return to the previous world. Dinosaurs, apart from birds, did not reappear. Large marine reptiles did not return. Instead, mammals expanded into terrestrial niches. Birds diversified into a wide range of forms. New types of plants spread, shaping landscapes in different ways. The direction of a life changed, not because it sought change, but because the old options were gone. It is tempting to frame this extinction as a dramatic overthrow, a sudden handover of dominance. That framing misses the quiet mechanics at work. Dinosaurs did not lose because mammals were better. Mammals did not rise because they were destined to. The shift occurred because environmental disruption removed certain forms while leaving others. What followed was an exploration of newly available space by those that happened to remain. Gentle humour can be found in how unspectacular this transition was at the time. The ancestors of future dominant groups spent long periods simply surviving, unnoticed, while the world around them adjusted. Their eventual prominence would have been invisible in the immediate aftermath. The fossil record captures this gradual change clearly. Diversity increases slowly, new lineages appear incrementally. Ecosystems regain complexity over millions of years. There is no sudden burst that announces new age. Instead, stability returns step by step. This extinction also illustrates how interconnected life is with the environment. The impact itself was brief, but its consequences spread through climate systems, chemical cycles, and food webs. Life responded not to the collision directly, but to the altered world it created. This distinction helps place the event within the broader pattern of mass extinctions. It was not unique in reshaping life through environmental stress, even if its trigger was unusual. In many ways, the Cretaceous-Paleogene extinction fits comfortably alongside earlier events. Long-term disruption mattered more than immediate damage. Survival favoured flexibility. Recovery took time. The living world reorganised rather than restored. Seen this way, the extinction becomes less about spectacle and more about continuity. Life did not end. It adjusted. It persisted through reduced light, cooler temperatures, and disrupted food chains. When conditions improved, it expanded again, guided by the survivors that remained. This perspective also tempers the idea of inevitability. There was nothing guaranteed about which group survived. Small changes in timing or geography could have altered outcomes. The path that followed was shaped by contingency as much as adaptation. History could have unfolded differently, had circumstances varied slightly. The Cretaceous-Paleogene extinction reminds us that Earth's history is not a march toward a predetermined present. It is a sequence of responses to changing conditions, shaped by loss, persistence, and chance. In the long view, the asteroid impact was a catalyst, not the full story. The true transformation occurred in the years and centuries that followed, as ecosystems adjusted to a darker, cooler, and less predictable world. Life endured that transition quietly. From those survivors emerged the foundations of the modern biosphere. Forests reformed, mammals diversified, birds spread across the globe, oceans regained productivity. The world moved forward, not restored, but renewed in a different form. The legacy of this extinction is written not in the moment of impact, but in the slow reshaping of life afterward. A reminder that even dramatic events matter most for how they change the environment and for how life responds once the dust has settled. In the periods following mass extinction, survival often belongs to those least noticed at the time, not the largest, not the most specialized, not the most impressive. Instead, it is frequently the small, adaptable, and quietly persistent forms of life that endure, continuing their routines while larger systems falter around them. After the Cretaceous-Paleogene extinction, this pattern became especially clear. With sunlight reduced and food chains disrupted, life entered a phase where efficiency mattered more than dominance. Large animals with high energy demands struggled to find enough to eat. Specialized feeders faced shortages when their preferred resources disappeared. In contrast, organisms with modest needs found ways to persist in a world temporarily stripped of abundance. Small body size played an important role. Smaller animals require less energy to survive. They can subsist on limited resources and recover more quickly when conditions improve. Many small mammals, for example, were able to survive on seeds, insects, and detritus when larger food sources became scarce. Their size also allowed them to shelter easily, retreating into burrows or dense vegetation to avoid temperature extremes. Birds, too, benefited from being adaptable rather than dominant. Some species could fly long distances to locate remaining food. Others were able to switch diets, feeding on seeds, insects, or carrion as availability changed. Their relatively small size and efficient metabolism increased their chances of enduring periods of scarcity. Like mammals, they did not thrive immediately after the extinction. They simply survived. Plants played an equally important role in this quiet persistence. Many flowering plants had developed seeds capable of remaining dormant for extended periods. When light levels dropped and growing conditions worsened, these seeds waited. Once conditions improved, they sprouted quickly, taking advantage of newly available space. This ability to pause growth and resume later proved invaluable in an unpredictable environment. Ferns offer a particularly clear example. After the extinction, fossil records show a temporary increase in fern spores, sometimes referred to as a fern spike. Ferns reproduce through spores that disperse easily and grow rapidly in disturbed environments. They were not the most complex plants, but they were excellent at recolonizing landscapes that had been cleared or damaged. Their success reflected opportunity rather than superiority. This theme repeats across groups. Insects with flexible life cycles survived more easily than those tied to specific host plants. Aquatic organisms that tolerated a wide range of temperatures and oxygen levels endured while more sensitive species vanished. Microorganisms continued cycling nutrients even as larger ecosystems simplified. What these survivors had in common was not strength, intelligence, or complexity. It was tolerance. They could make do with less. They could wait. They could adjust without requiring precise conditions. In uncertain worlds, these qualities mattered more than refinement. gentle humour can be found in how unimpressive many of these traits sound. Evolution did not reward grandeur or elegance in the aftermath of extinction. It rewarded being unremarkable, being flexible, being content with whatever resources happen to be available. It turns out that not standing out can be a useful survival strategy. Importantly, survival in the shadows did not immediately lead to dominance. For long periods, mammals remained small and relatively inconspicuous. Birds diversified slowly. Plants spread cautiously. The world did not suddenly become filled with new giants or complex ecosystems. Recovery followed the familiar pattern of patience. As ecosystems stabilized, these survivors began to expand. Mammals explored new feeding strategies and body plans. Birds adapted to a range of habitats, from forests to open areas. Plants diversified into new forms, shaping soils, climates, and food webs. What had once been background life gradually became more prominent, not through conquest, but through persistence. This transition highlights an important distinction. Survival does not require being exceptional. It requires being compatible with current conditions. Exceptional traits may help later, when environments stabilize and competition returns. But during periods of stress, adequacy often outperforms excellence. The fossil record reflects this clearly. In layers immediately following extinction events, diversity is low and dominated by generalists. Over time, as conditions improve, specialists reappear. Complexity builds gradually. The early stages are shaped by those who endured, not those who vanished. This pattern challenges common narratives about progress and success. It is easy to assume that life advances through a series of improvements, with better forms replacing worse ones. Extinction disrupts this idea. It shows that survival often favours traits that are practical rather than impressive. That being good enough can matter more than being optimal. Survival in the shadows also underscores the role of timing. Many of the lineages that later became central to ecosystems existed long before they became prominent. They were present, waiting, adapting quietly. When conditions changed and opportunities appeared, they expanded. Their later success was not inevitable. It depended on being there when the moment arrived. Plants in particular demonstrate this well. Flowering plants existed before the Cretaceous-Paleogene extinction, but they expanded dramatically afterward. Their ability to reproduce efficiently, adapt to varied environments, and form partnerships with animals allowed them to spread widely. This expansion reshaped landscapes, climates, and food webs, influencing the direction of life for millions of years. Yet even here, the process was gradual. Forests did not appear overnight. Grasslands took time to develop. Interactions between plants and animals evolved slowly. The foundations of modern ecosystems were laid quietly, through countless small adjustments rather than sudden change. The idea of survival through modesty extends beyond any single extinction. Across Earth's history, periods of stress consistently favour organisms that can endure uncertainty. Flexibility, tolerance, and low demands provide a buffer against change. These qualities may seem unremarkable during stable times, but they become invaluable when stability breaks down. In this sense, the survivors of mass extinctions are not heroes in a dramatic story. They are participants in a quieter one. They persist without attention. They continue routines that require little explanation. They form the background from which future diversity emerges. This perspective also reframes how dominance should be understood. The groups that come to define an era often do so not because they were the best competitors at the time of crisis, but because they survived when others did not. Their later prominence reflects opportunity as much as ability. History could have unfolded differently, had different survivors remained. Survival in the shadows is therefore not a minor footnote. It is a central mechanism by which life continues through disruption. When ecosystems collapse, it is the unnoticed forms that keep processes running. They recycle nutrients, they stabilize soils, they maintain food chains at a basic level. Without them, recovery would not be possible. As conditions improve, these quiet survivors provide the raw material for new ecosystems. They diversify, interact, and gradually build complexity. The shadows recede, but the influence of those who endured remains. In the long view, mass extinctions reveal a consistent truth. Life does not persist because it is impressive. It persists because it is adaptable. The survivors of these events did not anticipate their future roles. They did not evolve with dominance in mind. They simply continued, modestly and flexibly, until the world allowed more again. And from those modest beginnings, new eras quietly took shape. When the 5 great mass extinctions are viewed together, they begin to resemble variations on a theme rather than isolated disasters. Each unfolded under different circumstances, involved different organisms, and reshaped life in distinct ways. Yet beneath those differences, familiar patterns quietly repeat, revealing how the planet and the living world interact over deep time. One of the most persistent themes is climate. In every major extinction, long-term shifts in temperature played a central role. Sometimes the planet cooled, as it did during the Ordovician Silurian extinction. At other times it warmed dramatically, as during the Permian Triassic and the Triassic-Jurassic intervals. In the case of the Cretaceous-Paleogene extinction, temperatures dropped sharply after the asteroid impact before slowly recovering. The direction of change varied, but the effect was similar. Life struggled most when climates moved beyond familiar limits and stayed there. Climate change matters not because organisms prefer comfort, but because so many biological processes depend on narrow ranges. Metabolism, reproduction, growth, and behavior are all tuned to specific conditions. When temperatures drift steadily or fluctuate unpredictably, those finely balanced systems begin to fail. Over time, even small shifts can accumulate into widespread stress. Closely tied to climate is chemistry. Changes in atmospheric gases and ocean composition appear again and again across extinction events. Oxygen levels rise and fall. Carbon cycles are disrupted. Nutrients move differently through land and sea. These chemical changes often operate quietly, invisible in the moment, yet deeply influential. During the late Devonian extinction, oxygen-poor waters spread through the oceans, undermining reef systems and marine food webs. During the Permian Triassic extinction, warming and altered circulation reduced oxygen availability on a massive scale. After the Cretaceous-Paleogene impact, chemical changes followed reduced sunlight and disrupted productivity. In each case, chemistry shaped which organisms could continue and which could not. These shifts rarely act alone. Climate influences chemistry. Chemistry influences biology. Biology, in turn, feeds back into both. The spread of land plants altered weathering rates and nutrient flow, contributing to ocean changes. Marine microbes influenced oxygen levels, shaping the conditions larger organisms experienced. Across extinctions, it is the interaction between systems, rather than any single factor, that drives widespread loss. Another recurring pattern is time. Mass extinctions are often imagined as sudden events, but in reality most unfold over extended intervals. Even when a clear trigger exists, such as volcanic eruptions or an asteroid impact, the biological consequences stretch across thousands or millions of years. Life responds not just to the initial disturbance, but to the prolonged period of instability that follows. This long timescale explains why extinction feels uneven in the fossil record. Some species disappear early, others persist for a while before declining. Some regions are affected sooner than others. From a geological perspective, these changes compress into narrow layers. From the perspective of living organisms, they are gradual and cumulative. Time also governs recovery. In every extinction, life returns slowly. Ecosystems rebuild over millions of years, not because life lacks creativity, but because stable conditions must exist before complexity can flourish. Recovery requires patience, both from the planet and from the organisms adapting within it. A further pattern emerges in who survives. Across all 5 extinctions, survival tends to favour flexibility over specialisation. Organisms with broad diets, wide tolerances and modest needs are more likely to persist. Those tightly adapted to specific conditions often struggle when those conditions change. This does not mean that survivors are better in any absolute sense. They are simply compatible with altered environments. In some cases, survival appears almost accidental, shaped by geography or timing rather than by superior traits. A population located slightly closer to stable conditions may endure while another disappears. These chance elements repeat across extinctions, reminding us that history is not entirely shaped by adaptation alone. Circumstance matters. Another shared feature is that extinction reshapes dominance more than it eliminates life. Even in the most severe events, life does not vanish entirely. Instead, ecosystems are reorganised around what remains. Groups that once dominated may disappear, while others expand into newly available roles. Dinosaurs became prominent after the Triassic-Jurassic extinction, not through conquest, but through persistence. Mammals expanded after the Cretaceous-Paleogene extinction because they endured conditions that removed larger competitors. In this way, mass extinctions act as filters rather than erasers. They reduce the number of possibilities, narrowing the paths evolution can take. The future is built from survivors, not from what was lost. This constraint shapes the direction of life for millions of years, even when diversity eventually returns. Importantly, the patterns across extinctions challenge the idea of steady progress. If evolution were a simple march toward greater complexity or efficiency, mass extinctions would appear as setbacks along an otherwise upward path. Instead, they reveal a history that is branching, interrupted, and contingent. Complexity rises and falls. Dominance shifts. What seems advanced in one era may vanish in the next. Gentle humour can be found in how little nature seems to care about reputation. Entire groups that thrive for tens of millions of years can disappear, while humble, unassuming organisms persist and later shape the future. Evolution, it seems, has no loyalty to past success. Another theme woven through all 5 extinctions is interconnectedness. Changes rarely affect just one part of the system. Alterations in climate influence oceans. Ocean changes affect land through weather patterns. Plants alter soils and atmospheric composition. Animals shape ecosystems through feeding and movement. When disruption begins, it spreads outward through these connections. This interconnectedness explains why extinctions often appear global, even when triggers are regional. Volcanic eruptions in one area can influence climate worldwide. An impact in a single location can affect photosynthesis across the planet. Local changes propagate through global systems. Finally, there is a recurring rhythm to extinction and recovery. Stress builds, systems weaken, loss accelerates. Then, after conditions stabilize, recovery begins. This rhythm does not repeat on a fixed schedule, nor does it guarantee similar outcomes. Each extinction reshapes life differently, yet the underlying process remains familiar. Life absorbs pressure up to a point. When that point is exceeded, reorganization follows. Seen together, the 5 mass extinctions are less like isolated catastrophes and more like chapters in a long conversation between the planet and its biosphere. Earth changes, life responds. Sometimes that response is gradual, Sometimes it's abrupt. Over deep time, the interaction leaves a layered record of loss, endurance, and renewal. These patterns do not imply inevitability. They do not suggest that extinctions must happen on a schedule or that outcomes are predetermined. They show that life is responsive, constrained, and shaped by forces larger than any single lineage. Understanding these recurring themes helps place each extinction in context. It allows the focus to move away from spectacle and toward process, away from singular causes and toward interacting systems, away from endings and toward transformation. Across all 5 events, the lesson is not that life is fragile, nor that it is indestructible. It is that life exists within boundaries set by climate, chemistry, and time. When those boundaries shift too far, reorganisation follows, and through each reorganisation life continues, altered but persistent, carrying forward the imprint of what came before into whatever world emerges next. Across Earth's long history, one pattern stands out with quiet consistency. After even the deepest losses, life returns. Not immediately, not dramatically, and rarely in the same form, but reliably enough that recovery becomes part of the planet's rhythm. Understanding why life keeps coming back means looking less at strength and more at structure. Resilience in living systems does not come from a single dominant species or a perfectly optimized design. It comes from redundancy, from overlap, from many organisms performing similar roles in slightly different ways. When one disappears, others can continue the work, keeping basic processes running, even as ecosystems simplify. This redundancy is often invisible during stable times. In a healthy ecosystem, multiple species may filter water, recycle nutrients, pollinate plants, or break down organic material. They may differ in size, behavior, or habitat, but their functions overlap. This overlap can seem inefficient, even unnecessary. Yet during periods of stress, it becomes essential. When conditions change and some species disappear, others remain capable of maintaining those functions. The system does not collapse completely. It contracts, but it continues. This continuity allows recovery to begin once conditions improve. Diversity plays a central role in this process. The more varied an ecosystem is, the more likely it is that some organisms will tolerate unexpected change. Diversity spreads risk. Different species respond differently to temperature shifts, chemical changes, or resource shortages. What harms one may spare another. In this way, diversity increases the chances that life, as a whole, will persist. Importantly, diversity does not mean competition alone. While competition shapes evolution, cooperation and coexistence are equally important. Many organisms depend on each other directly. Plants rely on microbes to process nutrients. Animals depend on plants for food and shelter. Microorganisms recycle waste, making resources available again. These interactions form networks rather than hierarchies. When parts of these networks fail, others often compensate. After mass extinctions, ecosystems tend to reorganize around remaining interactions. Simplified food webs still function. Nutrient cycles continue, even if fewer species are involved. This basic functionality creates a platform on which complexity can slowly rebuild. Niches also matter. A niche is not just a place, but a role. It includes how an organism obtains energy, interacts with others, and fits into its environment. In diverse ecosystems, niches are finely divided. After extinction, many niches become vacant. Yet the conditions that created those niches often remain. Surviving organisms may expand into these open roles. They do not replace what was lost directly. They adapt existing traits to new opportunities. Over time, this expansion leads to diversification. as populations specialize within newly available spaces. This process helps explain why diversity often increases after collapse. Loss reduces competition and constraint. With fewer organisms occupying each role, variation becomes more meaningful. Small differences can lead to different outcomes. Over many generations, these differences accumulate, producing new species and new interactions. Balance returns gradually, shaped by what remains. Life does not rebuild by recreating the past. It assembles new arrangements from surviving parts. These arrangements may appear less impressive at first. Food webs are shorter, interactions are simpler, yet they are often more flexible, better able to absorb future change. Framing life as persistent rather than powerful captures this distinction. Power suggests dominance, control, and permanence. Persistence suggests continuity, adjustment, and endurance. Across mass extinctions, life rarely demonstrates power. It demonstrates persistence. It continues through modest forms, low demands, and quiet cooperation. Gentle humour emerges from this contrast. The organisms that carry life forward are rarely the ones that look impressive in textbooks or documentaries. They're often small, abundant, and easy to overlook. Bacteria, fungi, small invertebrates, and hardy plants form the backbone of recovery, doing unglamorous work that keeps ecosystems functioning. Without them, nothing else could return. Microorganisms are especially important in this context. They drive chemical cycles that regulate oxygen, carbon, and nutrients. They adapt rapidly to changing conditions. They occupy extreme environments where few others can survive. Through mass extinctions, microbial life has never disappeared, ensuring that basic planetary processes continue. This continuity provides stability beneath visible change. Even when forests vanish or reefs collapse, microbes continue recycling material, stabilizing soils, and maintaining atmospheric balance. Their persistence creates a foundation on which more complex life can eventually rebuild. Plants contribute another layer of resilience. By anchoring soils, capturing energy from sunlight, and forming the base of terrestrial food webs, plants shape entire ecosystems. Their ability to reproduce efficiently, spread widely, and tolerate varied conditions allows them to recolonize disturbed landscapes repeatedly. From these early plant communities, animal life can follow. Animals, in turn, contribute through movement and interaction. By dispersing seeds, mixing soils, and shaping vegetation through feeding, animals influence how ecosystems recover. Even simple interactions can have large effects over time, guiding the structure of emerging communities. Together, these layers form a resilient system built on cooperation rather than domination. No single group carries recovery alone. It is a collective process, emerging from countless interactions among organisms with different roles and tolerances. This distributed resilience is what allows life to endure repeated crises. Another reason life keeps coming back is that it does not rely on precision. Highly specialized systems can be efficient, but they are vulnerable. Life's long-term success comes from flexibility. Traits that allow organisms to function across a range of conditions increase the likelihood that some will persist when environments change. This flexibility is not about perfection. It is about adequacy. Being good enough in enough places is often more effective than being excellent in one narrow context. Over deep time, this principle favors persistence over optimization. Extinction tests this principle repeatedly. Each mass extinction removes options. Each recovery explores what remains. Over time, life becomes a patchwork of solutions, shaped by past losses as much as by present conditions. This history of adjustment is embedded in every ecosystem that exists today. Seen this way, life's return after extinction is not surprising, it is expected. As long as basic processes continue and some organisms endure, recovery remains possible. It may take millions of years. It may produce worlds very different from those that came before, but the underlying tendency toward rebuilding persists. Life does not come back because it is unstoppable. It comes back because it is distributed, cooperative, and adaptable. Because no single failure can eliminate all pathways at once. This perspective softens the idea of extinction without diminishing its severity. Mass extinctions are real losses. They erase lineages and reduce diversity, but they do not erase the capacity for life to reorganize. That capacity resides not in any one species, but in the collective structure of living systems. Across Earth's history, this structure has endured repeated stress. It has bent, simplified, and reshaped itself, yet continued. Life keeps coming back, not through force, but through patience, not through dominance, but through balance, not through power, but through persistence. When the idea of mass extinction is brought into the present, it naturally invites comparison. The question arises quietly, rather than dramatically. Are the patterns seen in Earth's deep past appearing again today, or does the modern world represent something different? Answering this requires care. Mass extinctions are defined not by concern or urgency, but by evidence preserved over long periods of time. They are recognized only after patterns become clear in the fossil record, across many environments and many kinds of organisms. This perspective alone places an important boundary around the question. Earth's past extinctions are understood fully only because enough time has passed to observe their outcomes. The present moment does not offer that distance. What can be said, carefully and factually, is that many species today are under pressure. Habitat loss, environmental change, and shifting climates are influencing ecosystems across the planet. Extinction rates appear higher than what is considered typical background levels. These observations are based on current data, monitoring, and historical comparison. At the same time, it is important to understand what these comparisons can and cannot tell us. Background extinction is not zero. Species have always appeared and disappeared. The fossil record shows a continuous turnover, even during periods of relative stability. The challenge lies in determining whether current rates represent a temporary increase, a sustained trend, or something that would eventually resemble a mass extinction when viewed far into the future. Scientists approach this cautiously. Rather than declaring outcomes, they examine patterns. How widespread are losses across different environments? Are entire groups declining together, or are changes uneven? How persistent are the pressures involved? These questions take time to answer, and the answers evolve as data improves. One of the differences between the present and past extinctions is speed. Human timescales are short compared to geological ones. Changes that feel rapid now may still unfold over centuries rather than millennia. Whether those changes continue, stabilize, or reverse matters greatly for how they are interpreted in the long view. Another difference is complexity. Modern ecosystems are deeply interconnected, not only biologically, but through human activity. Land use, transportation, agriculture, and technology link distant regions in ways that did not exist before. This interconnectedness can amplify stress in some cases, but it can also support resilience through conservation, adaptation, and management. Unlike past extinctions, the present includes awareness. Life on Earth has never before been studied by a species capable of reflecting on its own influence. That awareness does not guarantee outcomes, but it does change the context. Monitoring, protection efforts, and ecological restoration introduce variables that have no direct parallel in deep time. This does not place humanity outside nature, but within it. Humans are one influence among many, interacting with climate systems, ecosystems, and chemical cycles. Understanding this role requires humility rather than certainty. Earth's history shows that no single factor acts alone. Change emerges from interactions, feedbacks, and time. It is also important to avoid framing the present as uniquely catastrophic. Past extinctions were severe, but they unfolded under different conditions, over different timescales, and through different mechanisms. Drawing direct equivalents can oversimplify both past and present. Scientific caution means resisting neat narratives in favour of careful comparison. What evidence does suggest is that the present is a period of transition. Many ecosystems are adjusting to altered conditions. Some species are declining, others are expanding, ranges are shifting, interactions are changing. These patterns resemble early stages seen in past environmental disruptions, but resemblance is not destiny. Mass extinctions are identified in hindsight, not in progress. From within them, they would have felt like gradual change. Slight losses, shifting balances, familiar forms becoming rarer. Only later, when patterns were set into stone and fossil layers, would their full significance become clear. This perspective invites reflection rather than prediction. It reminds us that Earth systems respond over long spans of time, that outcomes depend on persistence as much as pressure, that complexity can both amplify vulnerability and support resilience. Gentle humour can be found in how uncomfortable this uncertainty often feels. Humans tend to prefer clear answers. Is this happening or not? Are we crossing a line? Earth's history offers fewer clean boundaries. It offers gradients, overlaps, and long transitions. The planet rarely announces what it is doing in advance. What can be said with confidence is that life has endured repeated upheaval before. It has reorganised under changing climates, altered chemistry, and shifting landscapes. It has done so slowly, unevenly, and without foresight. That history does not guarantee future outcomes. It does provide context. It shows that extinction is not a single switch that flips, but a process shaped by duration, extent, and interaction. It shows that recovery, when it occurs, takes time measured in millions of years rather than generations. It shows that the living world responds to pressure by adjusting its structure, often in ways that are not immediately visible. Placing the present within this framework encourages careful thinking. Rather than asking whether the world is ending, a more useful question is how systems are changing and which processes support stability versus instability. These are questions science is equipped to explore, gradually refining understanding as evidence accumulates. This approach avoids alarm without denying reality. It acknowledges that pressures exist while recognizing uncertainty about long-term outcomes. It allows room for both concern and perspective, without rushing toward conclusions that Earth's history warns against making too quickly. The present moment is not an echo of the past. It is its own chapter, still being written. Whether it will one day be described as another mass extinction is a judgment that belongs to future observers, looking back across time with evidence we do not yet possess. For now, what exists is change, variation, and response unfolding in real time. Earth's past teaches that such moments matter. It also teaches that they are complex. Life responds not only to loss but to opportunity, not only to stress but to stability when it appears. The outcome depends on interactions that are still in motion. Seen through this lens, the question becomes less urgent and more reflective. Not are we living through another one, but how does the present fit into the planet's long pattern of change? What can be observed? What remains uncertain? And how patience, evidence, and humility guide understanding. Earth's history offers no final answers, but it offers perspective. And sometimes perspective is the most grounding thing available. Extinction, when viewed across Earth's history, is often misunderstood as an ending, a failure, a stopping point. Yet the deeper the timeline stretches, the clearer another picture becomes. Extinction is less a final line than a turning of the page. part of a longer process that links loss, survival, and time into a single, continuous movement. Across the 5 great mass extinctions, life did not vanish. It changed, sometimes dramatically, sometimes quietly, sometimes in ways that took millions of years to become visible. What disappeared were particular forms, particular strategies, particular arrangements of living systems. What remained was the capacity for life to reorganize itself under new conditions. Time plays a central role in this perspective. On human scales, extinction feels absolute. The loss of a species is permanent, and that permanence carries emotional weight. On geological scales, extinction becomes one mechanism among many that shape how life unfolds. It removes certain paths while leaving others open. It narrows possibilities, but it does not erase the process that generates diversity. This does not make extinction trivial. Each extinction represents real loss. Entire lineages end. Unique combinations of traits disappear forever. The world that follows is irrevocably different from the one that came before. Acknowledging transformation does not soften that reality. It places it within a broader context. Seen through deep time, extinction functions less like a mistake and more like a reshaping. Life expands into available space. Over time, ecosystems become complex. They grow efficient, interconnected, and sometimes fragile. When conditions shift beyond what those systems can tolerate, reorganization follows. Extinction clears space not because the planet intends to, but because existing arrangements no longer fit the environment. What follows is not a reset, but an adjustment. Survivors persist with what they have. They spread into newly available roles. Over long spans of time, variation accumulates. New relationships form. Complexity returns, though never in the same pattern as before. The future grows out of what remains, not from what was lost. This process repeats across Earth's history with remarkable consistency. Cold, heat, shifting chemistry, moving continents, reduced sunlight. The specific pressures differ, but the response follows familiar rhythms. Stress builds, systems simplify, survivors endure, recovery unfolds slowly. From that recovery, new worlds emerge. Understanding this rhythm invites humility. Humanity occupies only a thin slice of this timeline, a brief moment in a history measured in billions of years. The living world did not begin with the present, and it will not end with it. Ecosystems have been reshaped many times before, long before humans appeared, and will continue to change regardless of individual species. This perspective does not diminish the importance of the present, it reframes it. Humans are participants in Earth's story, not its authors. One influence among many, capable of altering environments, but not separate from the systems being altered. Recognizing this position encourages care rather than certainty, responsibility rather than control. Extinction also challenges familiar ideas about success. The fossil record does not reward the strongest, the largest, or the most complex over the long term. It records persistence, flexibility, modest demands, the ability to function under a range of conditions. Traits that seem unremarkable in stable times often prove decisive when conditions change. There is gentle humour in this lesson. After millions of years of evolution, survival often belongs to organisms that ask the least of their environment. Small creatures, simple strategies, flexible habits. Nature, it seems, has a quiet preference for practicality over grandeur when tested. This does not mean that complexity is unimportant. Complex ecosystems are rich, productive, and resilient under stable conditions. They support remarkable diversity and intricate relationships, but complexity carries dependence. When those dependencies are disrupted, simplicity can offer a temporary advantage. Extinction reveals this balance clearly. It reminds us that life thrives not because it reaches a perfect state, but because it remains adaptable. There is no final form toward which evolution moves, no ideal arrangement that guarantees permanence. Each moment reflects a temporary balance between organisms and their environment. Framing extinction as transformation rather than failure helps clarify this point. Failure implies an expectation that was not met. Nature has no such expectations. It operates through interaction and response. When conditions change, outcomes change. Some lineages end, others continue. The system moves forward, altered but ongoing. This framing also highlights the importance of continuity. Even in the most severe extinctions, basic processes persist. Energy still flows, nutrients still cycle, microorganisms continue their quiet work. These underlying functions form the backbone of recovery, allowing life to rebuild when conditions permit. Without this continuity, recovery would not be possible. Life's ability to endure loss rests not on any single species, but on distributed systems, on redundancy, on cooperation, on overlapping roles. This collective structure allows the living world to absorb shock without collapsing entirely. Time then does the rest. Given enough stability, diversity increases, niches multiply, interactions grow more intricate. What once appeared sparse becomes complex again. The pace is slow, often imperceptible within any single lifespan, but steady when viewed across millions of years. This long view encourages patience. It suggests that immediate outcomes are rarely the whole story, that what appears diminished may still hold potential, that recovery is measured not in speed, but in persistence. Earth's history is filled with periods that seemed bleak from within, yet led to rich and varied futures. Extinction also reshapes how the present is understood. Rather than seeing the modern world as the peak of a long progression, it becomes one arrangement among many, contingent on past survivals, shaped by ancient losses. The ecosystems that exist today are not inevitable. They are the result of countless prior transformations. This understanding invites care in how change is discussed. It discourages simple narratives of decline or triumph. It replaces them with an appreciation for complexity, uncertainty, and time. It recognizes that Earth's systems respond slowly, unevenly, and in ways that often defy expectation. As this exploration of mass extinctions draws toward a close, what remains is not a sense of finality, but of continuity. Life has been tested repeatedly. It has simplified, reorganized, and rebuilt. Each extinction altered the course of evolution, closing some paths and opening others. None brought the story to an end. What extinction teaches about life is not that it is fragile, nor that it is invincible. It is that life is responsive, that it persists through adjustment rather than resistance, that it carries forward not through power, but through patience. The planet itself reflects this lesson. Earth changes gradually, landscapes shift, climates evolve, oceans open and close. Life moves with these changes, sometimes comfortably, sometimes under strain. Over deep time, the dialogue continues. Seen this way, extinction becomes part of Earth's long conversation with life. A pause, a redirection, a reshaping, never a full stop. As this chapter settles, the focus turns gently from loss toward perspective, toward the understanding that every living world is temporary, yet part of something enduring. That transformation, however difficult, is woven into the fabric of life itself, and that in the vast sweep of time, persistence matters more than perfection. As this journey through deep time begins to settle, the question of extinction no longer feels like a question of endings. Instead, it takes its place within a much longer rhythm, one that has shaped life on Earth again and again without hurry, without intention, and without finality. Across hundreds of millions of years, the planet has changed its conditions many times. Oceans have warmed and cooled. Continents have gathered and drifted apart. The chemistry of air and water has shifted slowly, then sometimes more quickly. Through all of this, life has responded not by holding still, but by adjusting. When familiar arrangements no longer fit, they gave way to new ones. Extinction, seen this way, is not an interruption in Earth's story. It is part of the pacing. Life expands when conditions allow. It becomes complex, interconnected, and specialized. Over time, that complexity brings both richness and fragility. When the environment moves beyond what those systems can tolerate, simplification follows. Some paths end, others remain. The living world reorganizes around what persists. This pattern has repeated quietly long before any single species could notice. What endures through every extinction is not dominance or strength, but continuity. Energy continues to flow. Nutrients continue to cycle. Microorganisms continue their unseen work. Even in the most disrupted worlds, the foundations of life remain active, waiting for conditions to stabilize. From those foundations, recovery begins, not quickly, not dramatically, but reliably. Reefs do not reappear overnight. Forests do not return all at once. Ecosystems rebuild layer by layer, relationship by relationship, across spans of time that feel almost unimaginable from a human perspective. Yet this slowness is not hesitation. It is the natural pace of complex systems finding balance again. Seen through this lens, survival becomes less about triumph and more about patience. The organisms that carry life forward are rarely the ones that draw attention. They are small, adaptable, and flexible. They tolerate uncertainty. They make modest demands. They persist quietly while the world around them changes. From their continued presence, new complexity eventually emerges. This quiet persistence is the thread that runs through all 5 mass extinctions. Each one reshaped the living world profoundly. Each one erased unique forms of life forever. And each one was followed slowly by renewal. Not a return to what had been, but the emergence of something new built from what remained. Understanding this does not diminish loss. It places it within a broader continuity. Extinction carries real weight. It closes possibilities permanently. The world that follows is always different from the one that came before. Yet difference does not mean emptiness. It means transformation. It means that the story continues, altered but ongoing. This perspective offers calm rather than alarm. Earth's history shows that change is not an exception. It is the rule. Stability appears, holds for a time, and eventually gives way to new conditions. Life does not resist this rhythm. It moves with it, sometimes struggling, sometimes flourishing, always adjusting. From a human point of view, this can feel unsettling. It challenges the idea of permanence. It reminds us that no arrangement, however familiar, is guaranteed to last. Yet it also offers reassurance. The same processes that allow loss also allow renewal. Life does not require urgency to persist. It does not rush. It does not plan ahead. It does not strive toward an endpoint. It responds to what is present, moment by moment, generation by generation. When conditions worsen, it contracts. When conditions improve, it expands. Over time, these responses accumulate into the vast layered history recorded in stone. Within that history, humanity occupies a brief moment, a single frame in a long sequence, important, meaningful, and consequential, yet inseparable from the larger systems that surround it. This position invites humility, not insignificance, but perspective, a recognition that the living world existed long before the present and will continue to change long after it. Extinction, in this context, is not a verdict. It is a process, one that reflects the limits of adaptation, the consequences of environmental change, and the capacity of life to reorganize rather than disappear. It reminds us that continuity does not depend on any one species' structure or strategy. It depends on distributed resilience and time. Time is the quiet partner in all of this. It smooths disruption. It allows recovery. It turns loss into transformation. Over enough of it, even the most dramatic changes settle into new balances. The fossil record, when read slowly, is not a chronicle of repeated collapse, but of repeated adjustment. Life persists because it does not need certainty. It only needs enough stability somewhere for something to continue. From that continuation, everything else can follow. This is why, after every extinction, the planet eventually fills again with movement, interaction, and diversity. Not because it must, but because the conditions allow it. As this exploration comes to rest, the antral theme remains simple and steady. Extinction is part of Earth's long rhythm. Survival is not loud or forceful. It is quiet, patient, and persistent. Life does not hurry toward the future. It waits for it to arrive. There is comfort in this rhythm. It suggests that change, while often difficult, is not the end of the story. That loss does not erase the capacity for renewal. That continuity exists even when forms disappear. In the vast sweep of time, life continues not through urgency or dominance, but through endurance, through countless small adjustments made without awareness or intent, through persistence that asks little and waits long. And so, as the night deepens and the mind grows quieter, the planet's history offers a gentle reassurance. Life has been reshaped many times before. It has simplified, reorganized, and returned. Each time, it has done so without haste, quietly, patiently, and always without urgency.